Yeah. So, hello everyone. You can see right now. And Jay has joined. And good evening. How are you? Okay, so it's almost halfway through the course, and you can give me some feedback and ask questions now. Okay, so let's begin with this live chat, and I see that now 5 people have joined. Uh, so uh, you can ask questions, any doubt that you have, or give us feedback about how the course is going, what you think of the course, and anything that you want to tell us. You will of course have to type into the chat because you cannot speak. Uh, so some of you had okay, somebody should take care of that part. If there is something that's how to be going and it's not so clear. Uh, so am I audible now? You can of course again post the questions you had posted in the discussion forum. If you want me to say something more about the queries which you had, bit earlier. Any specific question?
Silakan Bu Yesen.
Salam Pak Kapolri. And the students is saying that they can't hear their voice. They're right in the chat. Can you solve the issue? So my microphone is on. I was speaking to somebody there. People like stories like that. Huh. Yeah.
Ikutan biasanya, itu aku sudah jalan semua tuh biasa.
Okay, hello. Can somebody give me feedback? Can everyone?
Tidak bersama nangis.
So let me attend that you can hear me. Definitely, there's no question about it. Okay? Yeah.
off. On the laptop, I'm looking at the live session. The laptop speakers are off. Only I am connected from my iPad, and iPad. I'm in this meeting from my iPad, and that, of course, microphone and speaker are on. Yeah. I can start now. But I can't hear what you are saying there in that room right now. I can see you people, but I can't. Yeah. Hello. Hello. Yeah, I can see myself. Yeah, but no, it's not. Yeah, no, that is fine. I understand that. But the students are saying that I am not audible in the chat. Okay, all right. Yeah, okay. Yeah, thanks. Okay. I assume that they have resolved the issue. If I'm not audible, please give me a feedback. Okay, that's great. Ah, fine. So, okay, coming back to the question of generalized coordinates and generalized velocities being independent of each other. So here is the thing. In the Newtonian mechanics, when we talk about trajectories of the particle, it is typically goes like this. You describe the position vector of the particle along the trajectory as a function of time t, and all other quantities typically in quantum mechanics are associated with the time. That means when the particle is at one location at an instant t, you can calculate its velocity by taking a derivative of position vector. Then you can also calculate kinetic energy at that instant. So in Newtonian mechanics, the description is more in terms of time t and a given trajectory. But see what I'm going to do here. I want to now extend this idea of kinetic energy, which is a function of time t, to more general case. Okay. Now a particle visits a particular point in space, and then it has certain velocity, and then it has a typically kinetic energy or potential energy associated with that particular point, or potential energy associated with that point. But the kinetic energy, of course, would depend on how the particle is actually passing through that point, what its velocity at that moment is. Okay, so now what I'm going to do is I'm going to expand this in the Lagrangian mechanics, this construct in a following way. So there, of course, you have a Newton's equation as a second order differential equation, which is basically mass times acceleration is equal to force, and that describes a trajectory. Okay, or that's the differential equation of the trajectory. Now here what I want to do is this. I want to ask a question in a more general scenario. So the particle can take, infinitely many paths. And of these all, infinitely many paths, given a force field or potential field, which of these paths is a correct path? Is a question that we are trying to actually answer. And that's when we try to solve this differential equation. And that's when we come to a point where we expand the space from ordinary, space, the real space, three-dimensional space, to more general setting where I have now, if there are n degrees of freedom, 2n dimensional space where each point has n coordinates and n velocity numbers associated with it. If the particle visits that point in this particular setting, then it has a particular kinetic energy. So it's simply like, if you still want to make a picture in terms of Newtonian mechanics, a particle visits a point, and depending on how fast, it's traveling at that point, its kinetic energy will be different. So how many different ways in which the particle can pass that particular point? Infinitely many ways. It could actually come and stop there. It could, just be passing. It could be passing in a reverse direction. It could be passing with twice the speed, and so on. So particle could be traveling through a particular point with any arbitrary velocity, depending on its trajectory. And which of this trajectory is the correct trajectory is a question that we are trying to answer. Now, to make this possible, what I'm going to do is I'm going to take my kinetic energy, which was earlier defined as a function of time t, because I already knew the path of the particle. Now I do not know the path of the particle, say, and I want to define this kinetic energy for all possible paths, which means I want to define it at all possible points and with all possible velocities. Okay, so this is in some sense an extension of our earlier notion of kinetic energy, which was associated with the path of the particle. Now we're going to say that, well, to begin with, I know the force field, but I don't know which path particle is going to take, and I'm going to predict it. So I construct this, 2n dimensional space in which on the n axis I have coordinates plotted, and remaining n axis I have velocities plotted. And remember, in one of the lectures, the first, I forgot which lecture, but in one of the lectures I made it clear that a path in a configuration space, okay, path without any time element associated with it, is not really the trajectory, because we can just draw a path, but we don't know how fast the particle travels on it. So by adding this additional axis, now we are associating, velocities also with these particles, with these points. So this is how you extend the definition of kinetic energy, potential energy, if the potential energy depends on the velocities, and then you construct the Lagrangian. Okay, so this is the idea of extension of Newtonian mechanics to the Lagrangian mechanics. The domain over which Lagrangian is defined is, in some sense, 2n dimensional space. Okay, it's not 2n dimensional linear space, but it's a 2n dimensional space. Okay. Uh, does that answer your query? Yes. And of course, this idea of defining trajectories not just by giving a path in you know our ordinary three-dimensional or n-dimensional space, if we're talking about n degrees of freedom, extending it with velocities. You remember the idea of phase space that I talked about? This would be something somewhat similar to that, except that instead of velocities, instead of generalized momenta, the extra axis would be those of velocities there, generalized velocities. Yeah, so this oh yes, yeah. So what we are saying is that before we solve the problem, we don't know a specific path. So what I'm going to do is I'm going to define my Lagrangian over all possible paths. But all possible paths basically means the paths which are passing through this 2n-dimensional space rather than n-dimensional space. Because in n-dimensional space, if you do not give an additional time with it, then that would not make it into a trajectory. Yeah. And understanding this point is actually the sort of crux or crucial point of the entire Lagrangian framework. If you do not, truly understand the meaning of why Q and Q dots are independent of each other, then it would be a bit of a problem in understanding. Any other questions? It's free to ask any question. It doesn't even have to be associated with the course. Um, this is the first time we are actually meeting, so okay. Is there any specific class of functions on Lagrangian which oh no, of course. I mean, we did discuss this part in one of the lectures. That see, uh, basically Newton's equation gives you the second order differential equation in terms of the coordinates. Now we have extended this formalism to the Lagrangian formulation. Question is, do I have two separate Lagrangians which would give me exactly the same equation of motion as Newton's equation? And answer turns out to be yes. In fact, you already have written it in your comment there that if I construct a new Lagrangian by changing the gauge, and by gauge what you have written there as if you add a total derivative of a function to a Lagrangian, you will get a new. So basically, you have a Lagrangian. You take any arbitrary function f, take its total derivative and add it to your Lagrangian, well, it will give you exactly the same differential equation. Yeah, so in that sense, Lagrangian basically T minus V is a most convenient definition because that we borrowed from the Newtonian mechanics. But it's not true that this is the unique Lagrangian that gives me Newton's equations. There could be, the whole family of Lagrangians, which would give exactly the same, yeah. But you already have written that part there, the gauge transformation. This is called as a gauge transformation of Lagrangian. So you add, you know, so the basically this itself would form. Uh, okay, let me ask you this question. So the one part is a class of functions called Lagrangians. Okay, so are there, is a class of Lagrangians which give you exactly the same differential equation? Yes, there is, and they're connected to each other by the transformation which you have mentioned there. So any two Lagrangian, they give you same equation of motion. I should be able to find the capital F function that you have written there, because all I have to do is I have original Hamiltonian which I define it as L is equal to T minus V. I give you new Lagrangian which also gives me exactly the same equations of motion. I can take L minus L prime, and L minus L prime is equal to some df by dt. Can I integrate L minus L prime to get f? Yes, of course. Yeah. So this is the connection between the class. So equivalence will be defined through this particular gauge transformation. So capital F can be anything. Of course, Lagrangians can't be anything. Lagrangians are connected by df by dt. But then that f itself is arbitrary. It can be anything. Uh, yeah. No. There is basically uh, so all the other symmetry transformations could be put back into this gauge transformation form. So this is the most general way of connecting the Lagrangians. And I told you earlier that if you have any other Lagrangian, you could simply do L minus L prime and integrate that. Yeah. Any other questions from other students? Okay, looks like we can close the session now because nobody is asking any question now. Okay, thank you guys for being on this live session. In case you have any more questions, in fact, I wanted to make this comment for all of you that on this discussion forum, I'm seeing far fewer questions than I saw last year. In fact, last year, every day I was answering a few questions. But this time, the number of questions are too few. Uh, you can, of course, ask any question on the discussion forum, including the topics which we have covered, which we may not have covered in the course, but they are there in the other books there. Okay. Feel free to ask questions, and yeah, me and your other teacher Mrinal, both of us are answering these forums. Okay, in which case I will end this live session now.